Hey, now we're going to talk about Atwood's machines. An Atwood machine really is just a way to use force. It's really a lab apparatus that's designed to help us understand forces and accelerations. First thing you need to know is that tension is constant in a string. So if you have any type of string or cable, the tension is going to be the same throughout the cable, with one possible exception I'll show you later. And then also, if two objects are connected by a string, they have to accelerate at the same rate. So the tension is going to be constant and the acceleration is going to be constant. So we're going to use these rules and Newton's laws to solve problems involving simultaneous equations. So that's an Atwood's machine. It is essentially two masses held by a string over a massless, frictionless pulley. You can eventually add friction in, but we're going to stay away from that. We're going to say that the pulleys don't do anything to hurt the system or to help the system. Now, the tension in the string is constant, regardless of where it is, and the acceleration of the boxes have to be the same. So let's look at how to solve one. First of all, we have to adopt a sign for positive motion and negative motion, and then we have to be true to that sign. That's the key to solving them. And then we'll analyze each mass using Newton's second law and solve it. So I'm going to assume that that one's going to rotate that way. I'm going to assume that M1 is bigger than M2, so therefore M1 is going to cause the whole system to start to rotate. So M1 is going to move that way, M2 is going to move that way, and it's important that we keep that convention throughout. If you guess wrong, it's not a big deal. You'll just come up with negative values for some stuff. Remember, negative signs can indicate direction. So now we'll draw a free body diagram for each mass. We know what is the same. They have the same acceleration, they have the same tension. So now for mass 1, I have tension going up, I have M1G going down, the weight of it going down. I'm going to assume down is positive for that one because that's the direction it's going to go. And I'm going to now say the sum of the forces in the y direction are equal to m times a. So therefore M1G minus t is equal to M1a. Ignore that thing on the other side right now. It shouldn't have showed up yet. So it's the weight minus the tension. Remember, weight's in a positive direction, tension's in a negative direction. That's equal to M1 times a. Now that has two unknowns in it, so I can't solve it yet. So now I'm going to go to the other box. Well, I'm going to solve for t first. So I isolate t by itself. I get t is equal to M1G minus M1A. Now let's go to the other box. My free body diagram for that, tension is still acting up. M2G is still acting down. But in this case, the weight is going to go up, so I'm going to consider that to be positive. Sum of the forces in the y is equal to m times a. T, again, positive t this time because t is going up, minus M2G is equal to M2 times A. Now when I rearrange that equation and I'm going to plug in for t, M1G minus M1A. So algebraically, take a minute to write that down and make sure that you follow that. I've plugged that in for t. So now I have everything in terms of M1, M2, G, and A. I'm going to solve for A. A is equal to G times M1 minus M2 divided by M1 plus M2. So that allows me to solve for the acceleration. Now, the alternative way to do it is to look at the entire system as a whole. And now what I'm going to do is treat the whole thing as one. So I'm going to put all of that together. And I know that it's all going to accelerate. Now I'm going to consider that way to be positive. Now I do have a downward force M1G going down. I also have a downward force M2G going down. Now it's important if you're going to analyze the whole system that as a whole that you keep your sign convention right. So I'm now going to say the sum of the forces in the y direction are equal to M1 plus M2 times A. They have to accelerate together. The sum of the forces in the y direction are going to be M1G, that's positive, minus M2G. M2G is going up. I said down was positive. That's going to equal M1 plus M2 times A. Solve for A. Well, let's factor out G first. G times m1 minus m2 is equal to m1 plus m2 times a. It reduces down to the exact same thing you got before. So both of them will work. It really doesn't matter which one you go first. And of course, once you get the acceleration, you can then work backwards to get the tension in the string. Now, the maximum acceleration you could ever have, well, the maximum acceleration you can ever have without some other additional type of motor is going to be 9.8. So anything you get should be less than 9.8. If you solve a problem and get greater than 9.8, you probably have a sign wrong somewhere. So now let's solve for one. I have a 10 kilogram mass attached to a 3 kilogram mass. That way is going to be positive. 100 newtons down, 30 newtons down. So let's do the entire system method. Sum of the forces are equal to m times a. So I have 100 minus 30 is equal to 13 kilograms times a. So a is equal to 100 minus 30 divided by 13 kilograms. A is 5.4 meters per second squared. So the 10 kilogram is going to go down at 5.4. The 3 kilogram is going to go up at 5.4. So now, to solve for T, I'm now going to say the 100 Newton force acting down, T is going up, down is positive. Notice how my sign convention stays true. I'm now going to say the sum of the forces on the y equal m times a. So 100 minus T is equal to 10, which is the mass, times 5.4. T is equal to 100 minus 54, 46 newtons. So you've solved for tension, you've solved for acceleration. Now, if you have a ramp involved, it becomes a little more complicated. But it's still the same concept. You're still going to say the sum of the forces equals 0. And we'll do one of these in class. Hope this helped.